Dear friends, in this video, I am going to do a short masterclass on random forest, one of the very important machine learning algorithms. Let's now start. A random forest. You have a single tree, it will be a decision tree problem. Instead of single tree, you grow thousands and thousands of trees or millions of trees, a forest. So many trees are there. And if I combine, ensemble the learning of all the trees and then try to produce the desired output, it will be a fascinating exercise. So the philosophy of random forest is to build multiple trees. So this is the meaning. Now let's see. Why do you need random forest? A single decision tree does not perform well, even though it is super fast. Can we learn from multiple trees? When I say a single decision tree does not perform well, we will have to qualify this statement and justify this under what circumstances. A decision tree, when it is a single one in the typical way, when you grow and it is grown fully, you may have to prune because it may lead to overfitting. So you'll have to prune the tree when it grows out of proportion. Second, if there are some outliers in some of the features for certain records, then the decision tree results will be impacted by those outliers, and it does not have the full capability to address the variance part. It is in this context the random forest becomes very prominent and paramount. How do we learn from multiple trees? That question we will answer. But we believe learning from multiple trees will lead to better results. And we just want to ensure that the trees do not just learn the same, but give much more insights. And let us see. So what is this random forest? It's an ensemble technique. And it's very popular in view of its superior performance and scalability. So it's an ensemble of number of trees, thousands of trees, where each decision tree is built from what's called the bootstrap samples, K from N with replacement. If there are K records, I select N out of the K. Out of the K with replacement. That means I will have N raised to the power K samples. Because it is with replacement, I can select the same record again and again. So there will be N raised to the power K samples. K is, of course, less than N. And therefore, you do not take all the records to start with. You start growing the trees. Each tree is a subset based on the N sample, which is there. And the features are also, if there are 20 features, I may not take all the 20, I may take a subset, 5 or 6 at a time. So the subset of features, M out of P, without replacement is selected. That means I can keep on doing for each tree, the number of features will be the subset of the total features available P, and it improves the reliability of the model. The decision trees are normally grown deep without pruning. So to recapitulate bootstrap samples of K out of N with replacement, the number of features M out of P without replacement, and decision trees are built and several trees are there. We are going to learn how the output is reliable and elegant. The hyperparameters that will be required to be tuned to increase the model accuracy and reliability of the random forest are the number of decision trees, how many trees you want, number of records and features to be sampled, depth and search criteria, Gini impurity index or entropy, OOB, out of bag score or out of bag records, built-in validation sample, which is part of the random forest, an outstanding hallmark of random forest, OOB. Let's see its role, how it will help us. So let me take an example, a problem which is adapted from Bain Winston Marketing Analytics for discussion. A data set has 84 customers with two features: investment amount in $1,000, income in $1,000. Goal: predict whether a customer will subscribe to WSJ. Yes or no? WSJ is Wall Street Journal. So we are going to use the random forest. It's a small data set of 84 customers, and we straight away give it to the Python program and get the result. So first thing, I just submit the entire data set and let me see what it does. The idea is random forest reduces variance, and let's see the result. So when I subject the entire data set, accuracy is 100%, precision is 100%, recall is 100%, F1 score is 100%. The OOB score is 92.9, which is the accuracy is not 100%. We will look at the OOB shortly. So when I submit this as it is and apply the random forest, I'm getting this result. And the confusion matrix, since it is 100% accurate, there are 57 no in the original data set and 27 yes in the original data set, and all the 84 are correctly predicted. So the confusion matrix gives 100% accuracy. Now what happens is, even though random forest by its very nature does not overfit, but there is a danger sometimes when you use the training set and the test set. It could perform well in the training and it may slip in the test data. So we should not get carried away, even though accuracy is very important. And it's a small data set of 84, and we need to look at large data sets and all. But it tells a story. So what we do is, do we believe this? If I run a discriminant analysis or a logistic regression, will I get this? Of course, those models are not as good as random forest in accuracy, but they have better explanatory power. So the question the analytic professional must always ask is a trade-off between conservatism and optimism. So what is the most reliable way of looking at the problem? So here, random forest has the feature, the out-of-bag thing. Of course, the ROC, we can see 100% area covered. You can see that here. So let me just, this looks academic somewhat. So let me go to the OOB part. In random forest, each tree is trained on 63% approximately bootstrap sample of data. The remaining 37% approximately is OOB or left out for that tree. So each tree has 37% records left out for the OOB. And each record, in other words, is OOB for about 1/3 of the trees. 1/3 of the trees are OOB. So what happens here is each tree if I treat this OOB itself as a test data, which is the basic purpose, and validation data set, test data set, and aggregate prediction from OOB trees for all the trees that you have used in the random forest, of course, the computer will do the job. Equivalent in spirit, this OOB is jackknife method, but more efficient in practicality. So what is this jackknife method? Is it a technical term or a jargon? Let me explain this. The jackknife method is very popular in statistical modeling. What it does is, take this case, 84 records are there. You drop one record at a time. Suppose you drop the first record to start with. Build the model using the remaining 83 records or the observations. Then predict the outcome of the first record that is omitted using the model that you have built on the training data, which is 83 in number. Does the outcome tally with yes or no? Supposing a customer has subscribed to the Wall Street Journal, which is yes, does the model give yes or no? So you test it like this. Then omit the second record. Build the model from the remaining 83 and predict the outcome of the second record. So you keep doing this until all the 84 iterations are exhausted. Now, predict the omitted record and aggregate the results across the trees. That will be the jackknife validation. Because each tree, I would have done this 84 iterations and I would have got the prediction, aggregate them across all the trees. This is the famous jackknife method, one of the most reliable way of testing the model. But in practice, 84 numbers, it's okay, it's efficient, but it will not be able to withstand large data set and scalability is somewhat low. So in spirit, the OOB is the jackknife in practice. Therefore, what I have done is OOB-based confusion matrix, jackknife-based confusion matrix. I have put it here for the sake of comparison, and you may look at the data. 78 correctly predicted by OOB-based methodology, which is more realistic than all the 57 correctly predicted. The jackknife is 77. In this case, I would prefer the jackknife because there are only 84. Sample size is only 84, and therefore this is far more robust than OOB. But when I have large, I cannot do jackknife because it will be expensive, time consuming. I may not be able to also reach the solution. So in spirit, the OOB, which is 1/3 of the records reserved for test validation, can be used, and you generate the confusion matrix based on the OOB. This is what I do. In Python, you can write a script and get it rather than getting carried away by the initial findings. So my recommendation would be OOB you use for testing and the confusion matrix, and that OOB based confusion matrix is what is going to stand in reality. Okay, let me now display the performance metrics. OOB method, jackknife method, accuracy 92.9, 91.7, precision no, recall no, F1 score no. I put the numbers, but you know very well in analytics, we look at the S column because this is what we want to predict, and therefore precision, recall, and F1 score, I look at it for the S part. There are 27 S out of the 84, but of course the prediction part, it is correctly predicted, let's say 25 in OOB and 24 in jackknife. So when I do that, precision is 0.862. For OOB, jackknife, it is 0.857. Recall, it is 0.926 for OOB, and jackknife, it is 0.889. And the F1 score, which is a harmonic mean of precision and recall, is 0.893 and 0.873. Somewhat compatible numbers, but there is a difference of 2% here. There is a drop of about 7% here, 7 point something. And therefore, for small sample, in this particular case, jackknife, I would prefer, but OOB has done pretty well for large sample scalability. The most efficient way is the OOB. Now, how precision and recall are calculated, I have already explained to you earlier, and therefore I do not want to do that. You can refer the previous video. Now let's look at the relative importance of the features, which is based on the reduction in the Gini index, impurity index. Investment amount is 70% important, income is 30% important in determining whether a customer will subscribe to WSJ or not. Now, finally, the hallmark, a magnificent ROC curve, a comparative chart I have got for both OOB based on the jackknife and the area covered jackknife 97.2%, OOB is 97.3%, pretty close. Both methods show very high predictive power. Jackknife, unbiased estimate for small sample data. OOB, efficient and scalable for large data sets. And hence, I would recommend using OOB as the test data and get the outcome. And I would say it is wisdom to rely on the performance metrics and confusion metrics based on the OOB. And the remarkable technique, the random forest, it controls the variability part and overcomes the deficiency of the decision tree because it is an ensemble methodology which is ensembling thousands and thousands of trees, and across the trees it aggregates and get the results. And that's it. Thank you very much. We will see you in another video. Once again, thank you.